So for the case where we don't have a unit vector, it's very important to obtain a unit vector, because what's going to happen? So a given vector is going to have a magnitude. That magnitude will be multiplying with the value of the directional derivative. And for instance, if you don't unitize the vector, you may get, if you have a vector that is, say, 5 units in magnitude, 7 units in magnitude, well, yes, you're going to get a slope, but it's going to be multiplied by 5, by 7, and now think about it. Is it a slope of 2/3 equal to the slope of 2/3 times 5? It's going to be a lot steeper, right? So, and well, if you are hiking, for instance, well, that factor of 5 will be the difference between hiking and climbing, right? So that's what we're going to do today. So. Yes, again, the toy example we did last time was like a really nice type of example where we had a unit vector, just do the work, etc. All right. So now, what if we have like example number 2? We're given another surface 5y cosine of 2x. Find the directional derivative of f at the point 5/4 in the direction of the vector given by v 3i minus 6j. Well, this is going to change at this time because, well, just looking at the components of the vector, that's definitely not a unit vector. All right, that's not a unit vector. So, well, in this case, we would need to redefine this vector as a unit vector. So, for instance, well, let's get the magnitude for the vector, because again, we get a unit vector by dividing the components of the given vector by its magnitude. So, the magnitude of v, that equals the square root of 3 squared plus negative 6 squared, which will be a total of 9 plus 36, that equals the square root of 45. And you might want to simplify this number to 3 root of 5. Okay? So that is what is going to give us our unit vector. So let's obtain that unit vector. So u sub 1, no, not u sub 1, just u, which is the vector v divided by its magnitude. That is, I'm going to go back to component form, 3 negative 6 divided by 3 root of 5. So 3 over 3, that's equal to 1 over root of 5, that's 1 over root of 5. Comma, 6 over 3, that's 2, but minus negative, that's negative 2 over root of 5. Okay? And yes, I mean, if you find the magnitude of this vector, it's guaranteed that it's going to be a unit vector. Just think about it. 1 squared equals 1, negative 2 squared equals to 4, 4 plus 1 equals to 5, divided by the square root of 5 squared, which is also 5, boom, equals to 1. All right? So, what else do we do? Okay, let's find the partial derivatives. So, for the partial derivatives with respect x, that equals negative cosine of 2x, negative sine, not cosine, negative sine, 2x times by mini chain rule times 2. But that 2 times the 5y, that's going to be 10y. Okay? And the minus comes from differentiating the cosine, which is negative sine. So that's our partial derivative with respect x. For the partial with respect y, partial of f with respect to y, that equals, what's that? The derivative of y is simply 1 times everything else, which just works as a multiple constant. It's just going to be the multiple constant, 10. No, not 10, it's 5 this time. 5 cosine 2x. All right. So that's our partial derivatives. Well, so here is the thing. We need to redefine our directional derivative formulation. Let's go back to the previous page. So So when we define this, make some space in here first. So when we first define our partial, our directional derivative rather, so what did we do? So we multiply the partial with respect x by the cosine of the angle plus the, what's that? The partial with respect y times the sine. And makes sense because the cosine function again relates to the x values, the x points on the unit circle, and the sine function relates to the y values in the unit circle. So that's why you would see the connection, right? That's how you make the x component to be rotated or steered rather, and same for the y. Now here is the thing. Let's think about this backwards. Doesn't that result look a lot like a dot product? Doesn't that look like the result of doing a dot product between two vectors? What are those two vectors? So okay, so the direction of view of f, that is, those two vectors are the following: the partial with respect x, comma, the partial with respect y, cosine of the angle, sine of the angle. If you do the dot product between those two vectors, hey, don't you get this scalar right here? That scalar function, and this derivative happens to be a scalar, not a vector. So yeah, it's a rate of change, not a vector. It's a scalar. Okay. Now, well, but the simplest unit vector that you can come up with are those vectors whose components are values from the unit circle, like the one we got for the unit for the first example. You know, we did the cosine of 5 over 6 times 5 over 6. And we got numbers like root of 3 over 2, a half root of 2 over 2, common root of 2 over 2 if we were working with 45 degrees. If you were working, say, with pi over 12, then you would need to use the double angle or the sum and difference formulas to come up with crazy numbers that are still going to guarantee to be unit vectors. But those points in the unit circle, I mean, like the representative value, the special values like root of 3 over 2, a half root of 2 over 2, zeros and ones, are not the only possibilities for unit vectors. So we have to, in a way, detach from the trig idea, because in the end, we can still represent this directional derivative as the dot product between the vector that describes the partial derivatives and not cosine, not sine. Let me come up with a more generalized way to represent a unit vector. Call this simply u1 and u2. All right? Usually we use the letter u to denote a unit vector, which is what we did in the example. We were working. Now let's go back to the example. So, so if we were to use this idea for the example, because in this example we're no longer given an angle. I mean, of course, you can do arctangent. What's that? Negative 6 over 3. All right. And you're going to get an angle, but in this case, that's not going to give us exact numbers, because I'm pretty sure that's not going to be a nice number. It's not going to be a nice angle. So what are we going to do? Well, so instead use the new formulation using the components of the unit vector. So the directional derivative of f in the direction of u will be, at the point x, y, of course, will be the partial with respect x times u1 plus the partial with respect y times u2. Isn't that the result of doing the dot product between that new formulation for the what's it called, the directional derivative, except that I just changed the notation for the partial derivative to that of the Lagrangian instead of the Jacobian, and instead of having cosine and sine, I'm just using the generalized u1 and u2, which represent the components of a unit vector. Don't we have those components already? Here, there? Yep. Okay, let's get this directional derivative. Okay, so the partial with respect x, which is this expression here, negative 10y sine 2x, times the x component of the unit vector, which is 1 over root of 5. And again, you don't have to rationalize denominators here. That's fine. Plus f with respect y, that is 5 cosine of 2x, times the y component of the unit vector in the direction in which we want to obtain that slope, that derivative, right? That is times negative 2 divided by root of 5. All right? So, okay. So we have an expression already that is going to give us the slope in the direction of the given vector at your favorite point on the surface. Well, of course, as long as that order pair that we're given, it's in the domain of the function. So that's why we spent a good minute finding domains of functions to determine whether a given point is in the domain of the function, so we can differentiate at that point, so we can evaluate the function at that point, etc., etc. And well, I mean, what do we have? A polynomial in terms of y and a trig function in terms of x. So domain, it's all real numbers for x and y, so no problem. So for sure, this function is defined at pi over 4 of 1. So what are we going to do? Let's find the partial derivative, the directional derivative of the function f at the point pi over 4, comma 1 in the direction of the vector u, the unit vector u. That's what the subscript means. We're going in the direction of u. So let's just substitute the numbers. That is, substitute 1 for y and pi over 4 for x. That's it. So negative 10y times 1, which is 1 rather, sine of 2 pi over 4, which reduces to pi over 2 for later, times this 1 over root of 5, plus 5 cosine, 5 cosine of 2 times pi over 4, times, or rather let me do minus instead, and just multiply by 2 over root of 5. What is this going to give us? So, well, here, cosine of 2 pi over 4, that's the same as saying cosine of pi over 2, which goes to 0, right? Cosine of pi over 2, that's 0. All this term is going to go to 0. So we will be left only with only with this term that survives right here. That is sine of 2 pi over 4, that is sine of pi over 2, which is equal to, that equals to 1. All right? So that's going to leave us with the following, negative 10 over root of 5. I mean, if you want to rationalize, why not? This one is easy to rationalize. That is going to give us negative 10 root of 5 over 5, which is a negative 2 root of 5. All right? So in this case, what do we have? A negative derivative, right? What would have happened if we didn't come up with a unit vector? Well, the magnitude of this vector is 3 root of 5, or square root of 45. So we would have gotten a slope that would have been root of 45, larger than the actual slope. So that's why we need to make sure it's a unit circle. Okay. So that's another example of how do we compute the directional derivative. Let's talk about the gradient of a function of two variables, which actually we already look at that gradient. Well, what is this? What is the gradient? So number one, we need to make sure that the two partial derivatives exist at a given point, so we can find that gradient. So the gradient, which is going to be this vector, that is the first component of the vector, it's the partial of derivative with respect x for the given function, and the second component, the y component rather, it's a y, is a partial derivative with respect y. All right, and you have the two notations here, the Jacobian notation, Lagrangian notation. All right, you mind a new symbol? It looks like an upside down triangle or like an upside down uppercase delta from the Greek alphabet. This means nabla or del. So either name you want to give, it's fine. Okay. So but in this case, where we're looking at the gradient in the plane. Of course, there's a gradient in 3 dimensions, which we're going to get to look at later. And again, putting it all together, so actually another way to describe the directional derivative, that's now that we know what the gradient is, it's simply the dot product between the gradient vector and the unit vector in the direction in which we want to know that directional derivative, right? And of course, I mean, we already defined this vector right here. Now, just be careful because in this case, the input for the gradient is going to be a scalar. So we take the gradient of a scalar function, and the output is a vector. And this is, by the way, the first of the vector fields you're going to learn about. So, well, we're going to learn it. We're going to get into vector fields in the last chapter. Well, no, we haven't worked with vector fields. So far, we have worked with vector value functions. Vector fields are something else. All right, well, we'll see about that later. Okay, let's find the gradient for the function f of x. Y equals to y e to the x plus x squared y at the given point, which is 0, 2. Well, we're going to have a look at what the gradient means later, because we will look at some of these applications for the gradient. Well, so what do we need? Partial derivatives. So that is nabla of f. And by the way, make sure to put an arrow at the top because the result is going to be a vector. So that is given by the partial with respect x, comma, the partial with respect y. Okay? So let's find those partial derivatives. Okay, so the partial derivative with respect x, well, here we have y e to the x. The y just acts as a multiple constant. It's going to stay there. The derivative of e to the x is itself times the constant, that is y e to the x. The derivative of the second term with respect to x, that's just differentiating the x squared, which is 2x, times the y, which is also a multiple constant, that is plus 2x, y. Comma. So we're done with the partial derivative with respect to x. Let's find that with respect to y. So now we need to change the point of view for this function. Now we're differentiating the y. So to differentiate with y, it is the e to the x that acts as a constant this time. So the derivative of y, which is 1, times the constant e to the x, is simply e to the x. And over here, the derivative of y, which is also 1, is just the constant, which is x squared. So that is our gradient. All right, that's our gradient. Now let's evaluate this gradient at the point 0, 2. All right, so that's just plugging in numbers where they correspond for x and y. So that is y, which is 2 e to the 0 plus 2 times 0 times y, which is 2, comma, e to the 0 plus 0 squared. All right? That's going to result into, well, that's 0. E to the 0 is 1 times 2. That's a 2. And what else? E to the 0, which is 1 plus 0 squared, which is 0. That's just 1. All right? So that is a gradient. All right? But what is the gradient anyway? I mean, the partial derivative. No, it's not just the partial derivative. I mean, you can think of the gradient as a vector that stores information. Like in like in programming, how you work with vectors. Information separated by commas. So different parameters. Well, This can be thought of a database, if you will. But what is that? So the first component, again, is the slope in the x direction, while the second component is the slope in the y direction. So that's going to give us the slope in the y direction. All right. Okay, so let's have a look at another example to find the gradient. Okay, so well, actually, this two-part exercise is number one about finding the gradient, and part B to find the directional, the derivative. So that is, as you can see, again, this connection between the gradient and the what's it called, and the directional derivative. Let me just go back to the first page. You don't have to go back. Let me show you again. Let's recall how did we define this derivative, this directional derivative in terms of a dot product between two vectors. So rather than sticking to the trigonometric version, we just change the notation to a U notation, which denotes the components of a unit vector, right? And again, do the dot product between these two, you're going to get the new formulation we've been using. But again, what I want you guys to see is that we're finding the dot product between a unit vector and the gradient. So when I first did this, I didn't mention anything about the gradient. Now we know that it is the gradient indeed. All right. Okay, so let's go about this example. So for the function f of x, y equals to the arctangent of xy. So again, first of all, let's recall how do we differentiate the arctangent function. All right, that is arctan of u, in a more generalized way. That is 1 over 1 plus u squared times the derivative of u with respect x, or with respect y if we were differentiating with respect y, depending on the variable. But I mean, the rule, it's still going to be exactly the same. All right, so let's find the partials. That is the partial with respect x. That is 1 over 1 plus the quantity in parentheses xy squared times, careful, the partial derivative of xy with respect x. So the derivative of x there is going to be simply 1 times the multiple constant, which is y. That's going to be times y, which is going to give us, number 1, y over 1 plus x squared y squared. All right. Number 2, the derivative with respect y. That's going to give us the same, well, something similar, 1 plus, the first part, it's the same, xy squared. But in this case, since we're differentiating with respect y, the derivative of y over here is 1 times the multiple constant x will be the multiple constant x. And that's what we get by chain rule, so it multiplies outside. Okay, let's clean this up in a similar way we did. X over 1 plus x squared, y squared. So those are going to be the components of the gradient here. So let's write the gradient in component form. I mean, of course, you can use the linear combinations of i's and j's if you want, but I think it's better to go about the component form. That is partial of f with respect x, partial of f with respect y. So that is simply, just write down the results we got from before. Y over 1 plus x squared, y squared, comma, x over 1 plus x squared, y squared, right? So what do we need for gradients and directional derivatives? All the differentiation rules we learned back in Calculus 1 and Calculus 2. All right, all the polynomials, trig, hyperbolics, inverse trig, radicals, exponentials, logarithms, you name it. All right. Okay, so that was part one of the problem. Part B, find the directional derivative of the function at the point 1, 2 in the direction of the vector 3, 4. Which, by the way, careful. This vector right here must be a unit vector. And by looking at the components of this vector, it's definitely not a unit vector. I mean, 3 squared, which is 9, 4 squared, that's 16. Okay, 16 plus 9, that's 25. Square root of 25 equals to 5. So it's a vector with a length of 5 units. When we need a unit vector, again, how do we get a unit vector? Divide by the magnitude. So let's get that. Let's get the magnitude. Magnitude of v. That is the square root of 3 squared plus 4 squared. That equals root of 25, which equals to 5. Okay? Let's come up with a unit vector. Let's call this u. Right? That's the same u we see in the subscript of the directional derivative notation. Right? That is 3, 4 over 5. That's simply 3/5, 4/5. So that is our unit vector in the direction in which we're going to go to find the directional derivative. Okay. So how about, first of all, we evaluate the gradient we got in part A, the gradient that we got in part A, at the point 1, 2. That equals to, okay, number 1, so y, which is 2, over 1 plus 1 squared times 2 squared, comma, x, which is 1, over 1 plus, what's that? Another 1 squared times 2 squared. And we may go ahead and simplify this vector. That is 4 plus 1, that equals to 5. That's 2/5, comma, 1/5. By the way, that vector in the direction in which we want to find the directional derivative must be a unit vector. Again, let me reiterate that. However, this gradient, which gives us the partial derivatives in the directions of x and y respectively, that doesn't necessarily have to be a unit vector, because that's actually the first component. Again, that's the rate of change in the x direction, the actual rate of change in the x direction, and the y component is the rate of change in the y direction. So we need to multiply this by steering factors, that is dot product by a vector whose components are the components of a unit vector in the direction of a given vector, and that's going to give us the directional derivative in that direction. All right, let's go ahead and do that. That is du, okay, the derivative in the direction of u of the function at the point 1, 2. That's simply going to be nabla of f at 1, 2, that is the vector we just got before, and dotted with the unit vector. Okay, and we have all the information we need for this. Okay, so nabla of f at 1, 2, that's the vector 2, 5, 1, 5, I mean 2/5, 1/5, and dotted with the unit vector, which is 3/5, 4/5. And well, at this point you guys know how to do a dot product, right? So these calculations should be fairly simple. 2 times 3 equals to 6, 5 times 5 equals to 25, 1 times 4 equals to 4, 5 times 5 equals to 25, both positives, by the way, that adds up to 10 over 25, which reduces to 2 over 5, right? 2/5. Which is, but there's a funny coincidence here. The directional derivative in the direction of the vector 3, 4 is exactly as the slope, the derivative, which is the slope in the x direction. It's just a coincidence, right? It's not. It's nothing weird. It's nothing crazy. All right. So what's next? Applications of the gradient. Okay. So sometimes, I mean, think about when you're hiking. For those of you who like going hiking, well, you go to these trails, these pretty cool places, and there's already trails done for hiking, not for climbing, right? That's a whole different sport, if you will, right? Whole different activity. So, but in this case, if you are at a hill, okay, there's a way to determine in which direction should we go to go with the steepest slope, or in one direction or the other direction. That is, the slope or the direction of steepest ascent or steepest descent in the opposite direction. For instance, if you are on a hill, you're at the point, you want to avoid those directions because number one, you don't want to climb, right? Or number two, you don't want to fall. You don't want to slide, right? So, and you can potentially die of that, right? So you don't want that. So, and well, of course, when we go hiking, we don't know the mathematical function that models the hill we are hiking. Of course, we would use some common sense, right? If it's too steep, don't go in that direction, right? But in this case, what if we have that mathematical formula that describes or that models the hill or whatever surface, you know? Well, so let's have a look at this. Okay. So we have this surface right here, all right? And notice I'm choosing a point in this surface. That is the point A and B, all right? Whatever z value which is going to be on the surface, it's going to be this point right there, all right? And well, I know I wish I had instead like an upside down parabola that works better, right? But well, anyway, so. And you might wonder, what are these arrows here? Well, number one, they're vectors. So, but what are they in this case? So, number one, those vectors are the projections of these direction vectors on the surface, casting their shadows onto the xy plane. This is to help us see the situation. For instance, if we are at this point, okay, if we are at this point, let me draw a vector. So, at that point, we're going to have the following tangent line. All right, we're going to have that tangent line. Now, here is the thing. Again, a line in space. For the line in space, there's no such thing as rise over run. How do we describe a line? Don't we describe a line by the t variable being multiplied by the components of the direction vector, right? Well, so that's the direction vector which, number one, check this out, either goes in this direction or goes in the opposite direction, so goes in that direction. So this part right here, let me use some colors to highlight. Doesn't that look like it's going up with a somewhat increasing? It goes increasing, right? Looks like it's increasing. Its shadow is this, right? That's the shadow of this vector. Hey, what happened here? No, I don't want this. Okay, give me a second. I have to. And okay. There you go. So this is going to be the shadow of this vector in that direction. Now, do you see how also the line goes descending in the opposite direction? Okay, let me use a different color to highlight that part of the line. Okay, so highlight, and this is the corresponding shadow of that other part of the vector, all right? Okay, so from that point, we're going to decide, do we want to go in the direction of ascent or descent? Okay, so, and here is where our trigonometry, our calculus, and everything is going to help us understand what's going to happen here. Well, so number one, let's have a look at this expression, the directional derivative of the function f in the direction of the, again, we already redefined in a more generalized way as a dot product between a vector operation, that is the gradient of a scalar function, dotted with a unit vector, that is the direction in which we're going to go to find that slope, right? Well, how about we go back to the very beginning of the summer when we first learned about what was that? The dot product. Remember the definition of the dot product? Okay, so it involves trigonometry, right? That is nabla of f dotted with u. These two are vectors, by the way. So rather than writing the dot product component by component, I'm going to use the alternative definition, the one that allowed us to find the angle between two vectors, one involving trigonometry. That is, the product of the magnitudes, right, of these vectors, the magnitude of nabla of f times the magnitude of u, cosine of the angle theta, right? Because of course there will be some angle formed, right? Well, you'll see. But actually, we could simplify that expression. Do you see why we could simplify this expression? Why?
Because of the angle?
Not because of the angle, so... So we can simplify this expression. That's because, A, what is that equal to? 1, because it's not a unit vector. The magnitude of a unit vector is 1. So this will simplify to the following. That is, the magnitude of nabla of f times cosine of the angle. All right, let's talk about this function. Yes, we have crazy symbols here, the nabla, the double bars to denote the magnitude, but in the end, this is just the graph of the cosine function with a coefficient that will change the amplitude of that trig function if we see it from that point of view. That's all it is, okay? Now, let's do the calculus. Without doing the calculus, of course, because you know the properties of trigonometric functions. So, this function right here is maximized. When is the cosine function maximized? When theta equals to 0, right? So that means, okay, what is the value of the directional derivative? That is nabla of f, the magnitude of nabla of f, times cosine of 0, which is simply nabla of f. That's because, again, cosine of 0 equals 1. 1 times the coefficient, just the coefficient. But this special coefficient is, guess what? The gradient, nabla of f. Now, when is the cosine function minimized?
Pi over 2.
When theta equals pi over 2. Pi over 2? Over 2? Are we sure? So this is the graph of cosine. There's a minimum here, halfway between 0 and 2 pi, right? So that must be Pi, all right? It must be pi. Okay, so this is minimized when theta, when the angle equals to pi. That means, okay, what is it going to be? Let's compute or keep simplifying this. So the directional derivative, which is the magnitude of nabla of f cosine of pi. But what's cosine of pi? Negative 1, which will result into negative the magnitude of the nabla. All right? So, what is what is that going to mean? Well, these are magnitudes, so these are going to tell us the magnitude of steepest ascent and steepest descent. So, but now here is the thing: when is this directional derivative equal to 0? So we already looked at when it's maximized, when it's minimized, but when is it equal to 0? When is cosine equal to 0? Pi over 2, this time is the pi over 2. Okay, theta equals to pi over 2. Right? That means, okay, that means, nabla of f, the magnitude of it, cosine of pi over 2, which is 0. So but why do we want to know these values? Why are we looking at every single case? Interesting. Okay. Now, think about these two vectors here. Actually, these are two vectors that look a lot like a Cartesian plane, don't they? Where? So well, first of all, we need to establish an x and a y. So I know it's twisted because of the point on the surface, you know. However, let's pretend this is x and this is y. All right. Now, did you see the shadow of the green vector? Isn't that going into increasing, going in the increasing direction? What is this angle if this is the positive x-axis? Isn't that the 0 degrees? All right. Now look at the shadow of the same vector. Now going in the opposite direction. Isn't that going into the direction of descent? What's the angle? 3 pi halves. Well, this is x, this is y, so it's actually, what's the angle right here? 180 degrees. Oh, isn't that the same pi? We get a positive, we get a negative. So that's why we're getting the positive and the negative, right? Now, when is the directional derivative equal to 0? That means, or rather, why do we want to know when it's when the derivative equals to 0? That is, when theta equals pi over 2. Pi over 2, isn't that the same as 90 degrees? Do you see that picture here? Did you see this 90-degree formed by the two vectors? Now, let me come up with another vector. So, this vector in blue, right here, it's the shadow of a vector that is going in this direction. But why is that vector important? Because that vector is tangent. Oh, look at this. Is tangent to a level curve instead. All right? Now, think about what happens at a level curve. So if you're hiking, right? If you're hiking, you're just going around in circles or whatever the shape of the hill, all right? You're just going around, you're just going in circles. You're neither going up or down. That's what it means, right? Because it's a level curve. Remember how we describe those level curves as, well, in terms of applications, as isothermals or isometrics, I think it's called, for when you have the same height. I forget the name. So that's what this is the direction in which you would have to go, so that you're neither going up the hill nor going down the hill. All right? So now let's see these properties in a more formal way. Let's go to this definition box here. So, and again, We are given a function that represents that surface we're climbing, hiking, whatever we're doing. So, number one, if the gradient is equal to the zero vector, not zero, notice how it's voltage, it's the zero vector, then the directional derivative is zero. Because think about it, you will multiply those zero components from the gradient by whatever steering vector. 0 times the number plus 0 times the number, that's going to be the 0, so it's going to be flat, right? So no increase, no decrease. Number two, additionally, if the directional derivative is 0, so at any point this vector is orthogonal to the gradient, right? Because again, when the dot product between two vectors equals to 0, that means the two vectors are orthogonal, right? Yep. Number three, the direction of maximum increase is going to be the magnitude of the gradient at the point, and the direction of minimum increase or maximum decrease. So careful with the wording here. So that's going to be given by negative this nabla, which is what we did in the picture above, right? Case by case. So that all that is summarized here in this definition box. Okay, so let's have a look at one example to see this idea. So it's given the function z equals to x e to the y. Find the direction of maximum increase at the point 2, 0. Also, what is the maximum rate of change? Okay, so number one, let's find nabla. So this function z equals to f also, or simply call this nabla of z if you want, that's fine. So yeah, let me call this nabla of z. That equals the partial of z with respect x, comma the partial of z with respect to y. Alright, that is going to be, okay, partial derivative with respect x, that's 1 times the multiple constant, which is e to the y, that is e to the y, comma the partial derivative with respect y, that's itself e to the y times its a multiple constant which is there, which is x, that is x e to the y. Okay? So let's evaluate the gradient at the point, what was that? 2, 0, right? That is e to the 0, comma 2, e to the 0. What is that going to give us? E to the 0, which is 1. Okay? And 2 e to the 0, that's 2 times 1, that equals to 2. Okay, so earlier I gave you a different definition of the gradient. I told you it was just a database, right? That stores information. What kind of information? Number one, the rate of change in the direction of x and the rate of change in the direction of y. Now that we look at these properties of the gradient, we have a deeper meaning of this result. What is this? So that means that if I'm hiking a hill that is modeled by this function, so if I stand at the point 2, 0, that means that if I go in the direction 1, 2, that's the direction where it's the steepest, right? Which is the direction we want to avoid. Remember how I was talking about that? If we're going to learn how to find what's the direct, mathematically, how do we find that direction? Of course, in practice, we just use common sense, right? You don't go that way or the other way, okay? Otherwise, you have to climb or you're going to slide and goodbye, right? So, what is the maximum rate of change? So what's the value of the slope, the maximum value of that slope? Because for that we find, okay, maximum rate of change at the point. What's that? 2, 0. Well, here we need to find the magnitude of the gradient of f, well, in this case of z, at the point 2 comma 0. All right, that is, we find the magnitude of this vector, that is 1 squared plus 2 squared, that equals the square root of 5. All right, so we don't own, so the gradient doesn't always tell us what's the direction where the slope is the steepest. It also tells us what is the value of that slope, of that maximum slope, which in this case is, for this particular example, it's the square root of 5. Okay. What's next? Let's solve an application problem. Why not? Okay. So here is the thing. Of course, these functions give us the or represent the surface, for all points x and y in the domain. However, these functions may represent a density, a temperature density of amount density or density in general. Well, like in this case, this function right here, t of x, y, it represents the density, the temperature density of different points on a plate. All right, so and x and y are measured in centimeters. So that means, so let's say we are working in the manufacturing of metal plates. And of course, at one point in the process, they must get like really, really hot so they can get the actual shape. And let's suppose that we stand on a point on the plate. All right. So for this plate, I'm going to stand on the point 2, -3. From there, I have infinitely many directions to go. All right? And well, since you know the temperature density function, of course you want to avoid the direction where it's the hottest, all right? Well, that's what we want to know. What's the direction, in what direction from that point does the temperature increase most rapidly? And also, what is that rate? Okay, so number one, let's find the gradient, that is nabla of t, that is, let me just go directly to the partial derivatives. The derivative with respect x, that is -8 x, the derivative with respect y, -2y. All right, so let's find the what's it called, or evaluate the gradient at the point 2, -3. So this will be -8 times 2, comma -3, or rather -2 times -3. Okay, so this will give us what? -16, comma, what's that? -6, right? Oh, actually, this is negative. That becomes +6. Okay. What does that mean anyway? Okay, let's see. Let me graph this. And represent this plate on a Cartesian plane. So I'm going to do this to represent the plate. Now, from the point, let me go to the point 2, -3. The point 2, -3, which happens to be roughly 2, -3. Okay, so that means from there, that means if we go in the direction of the vector -16 units, 6 units, that is roughly that vector, that is where the temperature increases most rapidly, which is the direction you want to avoid, right? Otherwise, you're going to burn your feet, right? So, if I were to represent the temperature profile for this function, let me change colors here. So here is cold, so to speak. Then it gets a little warm, and then it gets a little hot. And here is in the direction where it's the hottest, right? So that is the direction you want to avoid. Now, what if the question here were, and that's a quiz question, in which direction should we go in order to cool down most rapidly? 16 negative 6, right? Quiz question, right? Now you got this, all right? Oh, but that's not the end of it. That's what's next. Then we also want to know how fast is the temperature increasing, or at what rate. So that is, find the magnitude of this nabla vector. That's the square root of negative 16 squared plus 6 squared, which results into the square root of 292, which we can simplify a little bit. I believe this is 2 times the root of 73. So that means that for every meter that we move in that direction, the temperature increases by 2 root of 73 degrees. And then 4, and then etc.
So the magnitude is the rate of change.
It's the maximum rate of change. If we go in the opposite direction, we would find, what was that? Negative, right?